some of them start real simple. Some you have to do a little bit more work with. So when you're doing a logarithm, one of the things I talked about is the answer to all these problems is an exponent. You know, that's a worthwhile thing to write down because it kind of helps you with your focus on a logarithm. Just you got to think about what the exponent is, but you got to be able to write this in exponential form. So the way that I was teaching this last time, this is a good approach to solving these problems, is just, write down the problem and set it equal to x. Just set it equal to a variable, okay? How do you write that in exponential form? What do we say? 4 to the x equals 64. Good. So that's what I'm saying, is the answer would be whatever this exponent is. Sometimes you can do that in your head. Sometimes you can't. So what is x in your head? 3, okay? Because we know that 4 to the third is equal to 64. Now, say a problem like this you can do in your head. You're just thinking, okay, what power of 4 is 64? All these problems are the same thing. This is what power of 9 is square root of 9. This is what power of 5 is 1. So you're looking at an exponent. I recommend that you just kind of do it this way. If you can do some of these simpler ones in your head, then I'm okay with that. So let's just do that. Let's just set that equal to x. Now, exponential form is going to be 9 to the x equals square root of 9, okay? So what is the square root the same thing as far as an exponent? What did you learn? It's what power? 1/2, good, okay? So what you'd probably want to do, you could either do that in your head, or you could just write that square root of 9 as 9 to the 1/2. And this is a common thing that shows up on these problems. We talked about this a lot last class. If the bases are the same, so if the bases are equal, then the exponents are equal. Okay, that's the basic idea. So x has to be 1/2. It can't be anything else. So the answer to that problem would be 1/2. And the reason is just because of this. The reason that's the right answer is because 9 to the 1/2 power is the same thing as square root of 9. Okay, does that make sense to everybody? Okay, you need to be really solid on how radicals change to exponents. That's real important. Okay, next one we'll do the same way. We do log base 5 of 1 equals x. If you write that in exponential form, we have 5 to the x equals 1. Okay, so what power do you raise 5 to in order to get 1? What power? 0. Okay, you know that anytime you raise something to the 0 power, you get 1. Okay, so that's the answer. The reason why that's the answer is because 5 to the 0 is equal to 1. Okay, and you can tell you're right on these problems. All you ever got to do is just go 4 to the third is 64, 5 to the 0 is 1, 9 to the 1/2 is square root of 9. Sometimes it's easy to do in your head, sometimes it isn't. The next problem is the one that takes the most work. And again, I would start with this one exactly the same way. I would write this as log base square root of 3, 27 equals x. Okay, and then we're going to work this one out a lot like we worked out b, but this one has a little bit more work involved. So you got to write this as square root of 3 to the x power is equal to 27. Okay, now we've talked about this quite a bit last time. The teacher designed this problem so it can be done this way because 27 is a power of 3. Okay, if that was like a 4, then I'd have to have something that's a power of 4 probably. Okay, so that's the idea. It's been designed so you can do this without having to use a calculator. So what you would do with this one is you can first of all write the square root of 3 as 3 to the 1/2 power to the x power. Okay, what's a good thing to do with the 27? 3 to the third, good. Okay, that's what we talked about last time. See, what you're wanting to do is you're wanting to apply this property. If the bases are the same, then the exponents are the same also. That's the idea. So what you would do here is you would multiply these exponents. So that's going to give you 3 to the 1/2 x is equal to 3 to the third. Okay, and then again, what we accomplished is the bases are the same. So therefore, we know the exponents have to be the same. So we would have 1/2 x is equal to 3, and then that's the equation you'd ultimately solve. So how do you solve that equation? Yeah, multiply by 2 to get rid of the fraction. Good. Okay, so you just multiply by 2. That's the easy way to do that. So it looks like what we'd have is x is equal to 18. Okay, like that. Now I'm going to run through and I'm going to show you why this, whoa, hold on. I think I'm thinking ahead. The answer is 6. I was getting ready to check the answer, and I realized there's no way that's right. Okay, so the answer is 6. Thank you. Okay. All right, so that would end up 3 times 2 is 6, so the answer is 6. My apologies. Okay, now I'm going to go ahead and show you why this is right. I think this is the key to understand logarithms, to understand why they're right. So let's do a check. This would be a good thing to write on your paper. Is what you would do is you would just take square root of 3 to the 6th power and see if that works out to be 27. Okay, without your calculator. You don't need to do this on your calculator. So one of the easiest ways to do this is there's a property that says if you have a square root to a power, you could just write that as the square root of 3 to the 6th. Now you could certainly take that on your calculator and you would get 27, I promise you. But remember, when you're doing a square root, you're doing half of that exponent. So the square root of 3 to the 6th is 3 to the 3rd, and 3 to the 3rd is 27. That's why it's right. That's the simplest way to wrap that around your head as to why 6 is the right answer to that problem. Okay, so everything on these problems is checkable. So when you're going to see problems like this on next week's exam, by all means, you want to check your answer and make sure that you're correct. It's all verifiable. And if you can do that, then you'll have it down to the extent that you want to have that down. Okay, is there any questions about anything I just did with anybody? Okay, that's just kind of a strategy to like to teach. Set it equal to x, write in exponential form. Sometimes they're doable in your head. Sometimes, like that last one, you got to play with it a little bit to get it to work out a certain way. Okay, so the next thing is the domain of a logarithmic function. So before I do anything with this, I want to show you a couple of things, and you don't need to write this down, but I want you to pay attention to this. So let's say, for instance, that you had, just for example, let's say that you had the log base 5 of 0. Okay, now let's see what happens if you tried to do this exactly the same way I did the problems we did before. So if you set that equal to x, then you would have 5 to the x equals 0. Okay, can you think of any number that you would raise 5 to that would give you 0? There isn't anything, okay? Because if you take like 5 to the negative 1, you get 1/5, right? 1 over 5 the first. If you take 5 to the 0, you get 1. In fact, if you take 5 to any power, you get a positive number. So this has no solution. Okay, that's what's important, is you can't do a log of 0 because it makes no sense. Now, I think a lot of times students have learned that, yeah, okay, you can't do a log of 0, but they don't know why. That's why, because that doesn't make any sense. Okay, let's do a negative number. Let's do the kind of the same thing. Let's say you have log base 5 of negative 1. Well, here's what would happen. You would do 5 to the x is equal to negative 1. Does that equation have a solution? No, and you got to understand that. I see this a lot of times even when I was teaching Calc 1 this morning. I can tell a lot of students didn't realize that that type of expression is always positive. If you take 5 to any power, you never get a negative number. Okay, does that make sense to everybody? So what this means is you can't take a log of 0 and you can't take a log of negative numbers. The only thing you can take a log of is positive numbers. You can write this little visual if you want to. Log of a positive is okay. Log of 0, bad, not okay. Reminds me of a Saturday Night Live sketch. Log of a negative is also bad, okay? So the only thing you can do is do a log of a positive number. That's the only thing that makes any sense. So when you're looking at what the domain of a logarithmic function is, that's what you got to keep in mind. So what I'm suggesting you do on this is, since the domain of a log of m is all positive numbers, what you're going to do on these problems is we're going to set the argument greater than 0 and solve. And what I mean by the argument would be the part in parentheses right there. You're going to set that greater than 0, and if you can solve that inequality, then you've got the domain. Now sometimes that's super easy to do. Sometimes it requires a little bit more complicated things to do. So to start with this example 1, the argument is x plus 2. What kind of number does x plus 2 have to be? Positive. So what you'll do is you'll set x plus 2 greater than 0. That's an easy inequality to do. What do? You just subtract 2 from both sides. And what you'd end up having on that is you would have x is greater than negative 2. So if you're going to write the domain on this, you got two ways to write it. You could say set of x such that x is greater than -2. That's your set builder notation, okay? And it's real easy to understand this if you think about it. What happens if you plug -2 in there? Don't you get a log of 0? Which is bad. You can't do a log of 0. What if you take a number bigger than -2, like say -1? -1 plus 2 is 1. It's okay to take a log of a positive number. So as long as x is bigger than -2, you're going to end up with a log of a positive number. Does that make any sense to you? Okay? So if you do this, take the argument set greater than 0, then if you can solve that inequality, then you've got it. Okay? Now that's a real basic one. The next one's, there's a little bit more to think about. So what we're going to do with this is, again, we're just going to write down 1 over x plus 4, and that's greater than 0 like that. Okay? Now this thing right here is a rational inequality. And with this one, you got to think about it kind of this way. Okay, you have to actually do a sign chart on this. Back when we were doing rational functions, I taught you how to do sign charts to figure out how the graph behaves. So first of all, this thing is undefined at x equals -4. So we're going to make a sign chart, and all that matters is that's -4. This thing is never equal to 0. So we're going to see where this turns out to be positive, and that'll give us the domain. Okay, so what we would do with this is we're going to use test points. Okay, let's take a point. Give me a number that's less than -4. -5. Okay, that wasn't what I was thinking, but it still works. Okay, all right. Plug it in to the function. Just go 1 over -5 plus 4. And then that would be 1 over -1, so that's a negative answer. Since it's negative, that's not what we're looking for. That would really mean that the graph is below the x-axis. So we don't want that. Now give me a test point bigger than -4. Okay, -3, 0 is good, whatever, it doesn't matter. It'll always give the same result. Let's plug 0 in. Then you'd have 1 over 0 plus 4. That's equal to 1/4. That's a positive number, so that's what we want. We want this to be positive, okay? So what's the domain going to be based on that sign chart? From where to where? -4 to infinity, right, okay? So what you could do on this, you could write this in two ways. You could say set of x. You could say x is greater than -4. It can't be equal to -4 because you have a 0 denominator. Or you could write that as -4 to infinity like that. Okay, same thing with this problem. You could also write that as -2 to infinity like that. Now, how did I know to do a sign chart? Because that's a rational function. Okay, you can't just get x by itself on the side. It won't work. So what you've got to do is you've got to go to that sign chart. So you have to do that a lot of times when you're figuring out domain. Okay, so that would be the basic idea behind that. All right. Okay, is there any questions what I just did? That's the harder one right there. That's the one students a lot of times don't understand very well. Okay, the rest of these are going to be kind of the same thing. So here's what you're going to do on this one. So again, we're trying to find the domain. The argument is what you're taking the log of. So what you're going to do is you're going to take that argument, write it down, and set it greater than 0. Now, you could think about this and do this in your head. You really could. We're going to do a sign chart on this because I think you'll understand it better. But I'll show you in a minute how you could do this in your head. Okay? So let me do that first of all. Okay, what happens if you square any number? What do you get? You get a positive, right? But you could get 0, right? Okay? So it looks like no matter what x is, since you're squaring it, you would get a positive. But what would make that 0, just in your head, just the inside part? Yeah, so if you had -1 plus 1, that would be 0. 0 squared would be equal to 0. The answer to the problem is actually going to be all real numbers except -1. And that's because when you square something, that's guaranteed to be bigger than 0, with the exception when x is -1, when you get 0. Tell me if that makes any sense or not. Okay, now I'm gonna do the sign chart because, ultimately all you got to do on this problem is what you're going to do is you're just going to set that equal to 0 and solve the equation. Now, you don't have to do this because you can do this in your head. That would give x plus 1 equals 0. Therefore, x is negative 1. So on our sign chart, what I'll have you do is we'll just look at negative 1, and then we'll do test points, and I'll show you what happens. And the same thing is going to happen as what I was trying to show you in your head. So what's a good test point to use below negative 1? Negative 2. Okay, let's plug in negative 2. So do negative 2 plus 1 to the second. And that's going to give you negative 1 to the second. Is that positive or negative? Positive. That's what we're looking for. That's exactly what we're looking for, is where that's greater than 0. So that's what one of the regions we're looking for. What's a good test point on the other side of negative 1? 0, 1, whatever you choose, as long as it's bigger than negative 1. So if you plug that in, you would have 0 plus 1 to the second, and that's 1 to the second, so it's also positive. So what would happen is, we're trying to figure out what kind of values of x cause this to be positive. Well, everything there, the only problem is that number right there. So what you would end up saying for your domain, you can write your domain in one of two ways. You could say set of x, and you could say x is less than negative 1, or x is greater than negative 1. Okay, it can't be equal to negative 1 because then you would be doing a log of 0, which you can't do. Okay, if you wanted to write this in interval notation, you would say negative infinity to negative 1, parenthesis, union negative 1 to infinity. And all that interval notation is doing is just saying, okay, everything's set to negative 1. That's what the purpose of the parentheses are on that problem then. Okay? Okay, does that make sense? Okay, those are the little details you got to be very careful about. Yes?
Is there a reason that you can't just say x is not equal to negative 1?
Oh, you could say that too. If you said, like in set builder notation, if you just say x, set of x, that's also fine. Whoops, not, you said the right thing. I wrote the wrong thing down. Because that's just implying it's everything but that. So that's also okay. All right? Okay. Next one's actually easier. So let's see. What are you going to set up on this problem to figure it out? First step, what do we do? Take the argument and set it greater than 0, right? Okay, it's always the same. Whatever's in parentheses, greater than 0. Okay, now you don't need a sign chart for that. Can you solve that for x and just get x by itself on the side? Yeah, so you don't need a sign chart. You could make a sign chart if you want to. It's just unnecessary. So all I'm going to do with this is subtract 5 from both sides. That's going to give 2x greater than negative 5. Then if I divide by 2, I get x is greater than negative 5 over 2. So as long as x is bigger than that number, then you're going to have a graph. And I'm going to do something on this on the graphing calculator in just a second too. So you could write this either as set of x, such that x is greater than negative 5 halves, or you could write it just as negative 5 halves infinity like that. Okay? Now get your calculator out. So I want you to run through this one on the calculator. I think all these things can be looked at on a calculator. So what I'm going to have you do is we'll go to the y equals. Let me clear off the junk I got on there. Just put in what we're looking at. We're looking at the natural logarithm, so press your LN button, of 2x plus 5. Now we're just going to graph that in the standard window, and it's actually very easy to make sense of the graph we did. So you can go zoom number 6, and then it'll graph right there. Okay, remember what we found was x has to be bigger than negative 5 halves. Negative 5 halves is negative 2.5. Where does it look like the graph starts? Around negative 2.5. That's exactly what's happening. So what you'll find on this is whenever you're bigger than negative 2.5, then you have a graph, but everywhere else you don't have a graph because it's undefined. If you went like second table of values, what you'll see on this, on your table of values, is once you get below negative 2.5, you're just going to start seeing errors all the way, because then you're doing logarithm of negative numbers, which is undefined. Okay, so you can look at these things visually and pretty well tell you're right. Okay, and that's something that I'd recommend that you do, but you want to be able to figure those domains out without having to just go to your calculator, okay, because that'll help you understand this better. Okay, any questions about what I just did? Okay, the big deal on that is sometimes you have to use sign charts, and typically you have to use sign charts when you have powers, like a second power or higher, or if you have a rational function like that. That's when you're doing sign charts. Every other thing, like if your highest power is a first power, like 1 and 4, you just solve an inequality the standard way. Okay? Okay, next thing we're going to look at, and this is real important, this is something that I always like to give on a test, so you might want to put a note by there. This is kind of like this is a very typical test question because this is so fundamentally important that you want to know and understand this. So what we're going to do is we're going to graph these two functions, okay? And to start off with, we're going to start by graphing y equals 2 to the x. All right, and so what I'm going to do on this is we're going to do x and y equals 2 to the x. We've already did this. We did this in a I think 6.3 is where you start learning about exponential functions. So what kind of numbers could I use for x? Is there anything x can't be? Yeah, it can be an exponent can be any number, right? It can be negative, it can be 0, it can be positive, it can be anything. So I would suggest that you just do real simple numbers, 0, 1, 2, negative 1, negative 2, like this. We have graphed this before, so it's just kind of a review of that. Then we're going to just work these out. So we're going to plug in like 2 to the 0, that's 1. 2 to the first, we know is 2. 2 to the second is going to be 4. Okay, now go to your negative exponents. When you do 2 to the negative 1, what do you get? 1 over 2 to the first, right? And you can do that in your head, but remember you're changing that exponent to positive, so you got a half. And then the same thing with 2 to the negative 2, that's 1 over 2 to the second, so that's 1/4 like that. That should look familiar to you because we've done that and already worked that out. You've already done some homework on that too. So let's go ahead and let's plot these points. Just kind of I'm going to start with 0, 1. So 0, 1 is a dot. We have 1, 2, and we have 2, 4. It would be helpful if you labeled those points for what we're going to do. So that's 2, 4, that's 1, 2, and that's 0, 1. Now what happens is the graph kind of turns up and goes like that, and then it just levels off at the x-axis. So if you have negative 1 1/2, you got that. Negative 1 1/4, you just want to show that that thing is approaching the x-axis. So that's the graph of y equals 2 to the x. Okay, and that's an easy table of values to make. Okay, now what I'm going to do on this is I'm going to show you something. We're not quite ready to establish this yet, but on the next graph we're going to do y and we're going to do log base 2 of x like this. All right, now what I'm going to have you do on this, and I know what's going to happen, you may not know this yet, but I'm going to have you do the y values. So we're going to bring these y values down. That's a 1/4, that's an x, so we're going to use a 1/4, a 1/2, 1, 2, and 4 like that. Okay, and you don't want to use any other number because then you'll end up getting some stuff that you won't be able to do unless you have a calculator. Okay, so I'm going to start right here in the middle. So we're going to do log base 2 of 1. Okay, now we want to be able to figure this out in our head. All right, so remember what you can do is set that equal to x, and then you can say 2 to the x equals 1. Okay, so what would be x in this expression? 2 to what power is 1?
0.
0, okay, so that's got to be 0. It's got to be. Okay, now we're going to keep crunching this out because I want you to see something on this. Okay, you may already see it, depends on you. So let's go log base 2 of 2. So we're going to do the log base 2 of 2, set that to x. If you write that in exponential form, you'll have 2 to the x equals 2. So what does x have to be in that?
1.
Are you seeing anything? What's happening to these points? Yeah, they're backwards. Okay, there's a reason why the teacher picked these numbers. Okay, let's keep crunching them, make sure. So this next one is log base 2 of 4. Okay, so I'm going to set that equal to x. I'll write that as 2 to the x equals 4. So what does x have to be in that equation? 2. Okay, see what's happening? 2, 4, 4, 2, 1, 2, 2, 1, 0, 1, 1, 0. What do you call that? Call that an inverse. Good. So these things are going to end up being inverses of each other. Let's crunch the next two out because it's a worthwhile exercise to do. If you did log base 2 of a half and set that equal to x, you would just have 2 to the x is equal to a half. Well, x would have to be -1 because 2 to the -1 is 1 over 2. So that's -1. So are you convinced now? Can I just put the next one on here? Is that good enough? Okay, you can crunch every one of those things out and you get that then. So yeah, what I wanted to see is 2 to the x and log base 2 of x are inverse functions of each other. And I'm going to go through that a little bit more in depth here in just a minute. But let's go ahead and let's plot these points. So if we plot this, we'll have a point 1, 0. I'm going to label these points as I go. Then we have a point 2, 1, just whatever will fit on here. Then I have a point 4, 2, like that. So this graph is going to kind of go up like that. And then if you plot these other points, like 1/2, -1 is there, 1/4, and you're going to find on this what's going to happen is you're going to end up just having an asymptote on here. I don't know what's going on there. Okay, so that's going to go down something kind of like that. All right? So when we studied inverses, do you guys remember what they're symmetric about? There's a special line that it's symmetrical about. Do you remember anything about that? Y equals x. Okay? So the other thing that's worth writing on your paper, just kind of draw a dashed line, and that's y equals x. So it's symmetrical about that line, so it's got the kind of symmetry you would expect to have. So what'll happen is if you're graphing the log base 2 of x, well, you don't want to just use any old number. You want to use like powers of 2, like 2 to the 0, 2 to the first, 2 to the second, 2 to the -1, 2 to the -2. If that was a log base 3, you wouldn't just pick any old number for x. What would you use? 3 to the first, 3 to the second, 3 to the 0, 3 to the -1, 3 to the -2. Okay? So if you're graphing a logarithmic function, your x's need to be powers of that base. Does that make any sense to you? Okay? If you don't do that, you're not going to get anywhere on the problem. Okay, so another thing I want to look at on this is we want to look at the domain of 2 to the x. So look at the red function. That's the exponential function. What does it look like the domain of 2 to the x is? In other words, what can x be?
Greater than 0.
It can be 2 to the x can be anything on this, right? Because your exponent can be any number. An exponent can be any number. So the domain is going to be all real numbers. Okay? What that means and what we learned is we do that. Okay, now the range is going to be on the red function. What's the range? What can y be? It's got to be 0 to infinity. It's got to be positive numbers. Okay, so we have that. Now what we learned is, since we now know their inverses, is we learned that the domain of the function and the range of the inverse have to be the same. So I want you to look at the green graph. Does the green graph look like it goes to -infinity and to infinity? Okay? All right, and we also learned that the range of a function turns into the domain. Okay? So that means the domain is just going to be that, so that's 0, infinity. Now look at the green graph. Does the green graph look like it starts at 0 and goes to infinity? Yeah, that matches up. So that domain is this. That range is all real numbers. That's something that we learned when we were talking about inverse functions. Okay, since we're switching variables, the domain of the function turns into the range of the inverse, and so forth. Okay, all right, one other thing I want to show you on this problem, you may be running out of room, but try to squeeze it in if you can. We're going to find the inverse, even though we already know what the inverse is. We're going to find the inverse of y equals 2 to the x. Okay, I just showed you that it is. Now I'm really going to prove it. Okay, so when we do an inverse, and you've already done some work on this and done some homework, what do you do to the variables y and x? You switch them, right? So the first thing is you want to just write that as x equals 2 to the y, like that. Now what you're going to do is you're going to write this in logarithmic form. Okay, so if you write this in logarithmic form, that's the base, so that goes there. Remember, the answer to a logarithm is an exponent. That exponent is y, then the x goes there. Okay, so if you take that x equals 2 to the y and write it in log form, you're going to get that. So that's what the inverse is. So that would be, we'd say, f inverse of x like that. Okay? All right, one thing that's kind of a typical thing that I like to do on exams, because it's real important, is just something like this where you're doing an exponential and graphing the logarithm that goes with that. Okay? And I can't change the problem very much. I can say 3 to the x, log base 3 of x. I can say 4 to the x, log base 4 of x, and so forth. But that's a real fundamental part of learning logarithms and their graphs, is to understand that they're inverses of the exponential. Okay? Okay, let's move down to the bottom here. Now this is just kind of saying what we did. This is just saying if you do a domain of a log, that becomes the range of the exponential, and the range of a log becomes the domain of the exponential because they're inverses of each other. Okay? Okay, so we're going to do kind of work on a few more graphs that are like this. So to begin here, we're going to go ahead. We've already learned the graph of y equals e to the x, but I'm going to have you just kind of recreate a table of values here. Okay? 2 to the x, e to the x is going to look almost the same as 2 to the x because e is like about 2.7. So it ain't going to look much different. Okay, what we're going to do is we're just going to use kind of the same typical numbers. We're going to do 0, 1, and 2. We'll use the calculator to make a couple of estimations on this too as we go through this. Okay, so we're going to start off this way, then we'll also use -1 and -2. Okay, so the first one you have e to the 0. What's e to the 0? 1. Anything of 0 is 1. Then we have e to the first. Okay, if you don't remember this, you could go second, right above ln gives you your e to a power key. You could put in e to the first, and that'll give you about 2.7. Okay, that's pretty important to know that e, at least know it to one decimal, 2.7. Okay, then you could go e to the second, just to get an estimation here. So that e to the second is approximately 7.4 like that. Okay, then if we go to the rest of them, we have e to the -1. Well, just write that as 1 over e. That's just going to be a number that's between 0 and 1. Then if you do e to the -2, that's going to be 1 over e squared. And that's good enough because all that's going to say is you're approaching the x-axis like on the last problem. So let's go ahead and let's plot these 3 points and get this put together. So we'll have a point 0, 1. Let me zoom on this a little bit better so I can see what I'm doing. Okay, then we have a point 1 and up about 0.7, over 2 and up about a little bit bigger than 7. Okay, so you'll have something kind of like that. Then you do that. And then what will happen is it'll approach the x-axis like that. That's what the 1 over e squared and the 1 over e, it just says as you're going further to the left, as x gets smaller, you're approaching the x-axis but never reaching it. So you probably want to label that as y equals e to the x. Okay? So what we are going to do next here is we're going to do the log function. Okay? So what we want to do on this is, again, if you're going to make a table of values for y equals ln x, don't just use any number for x. Don't do that. Remember on the last problem, what did I do? I used powers of 2. 2 to the 0. And do the same thing here. Do like e to the 0, e to the 1, e to the second, e to the -1, e to the -2. So you know these things are inverses. So these are the best numbers to use, is those numbers right there. Okay? So that would be the best things to use for e would just be these. Okay? Now e to the 1 is about, e to the 0 is 1. So what's going to happen if you do the natural log of 1? All that means is e to the x equals 1. So that means 0. That's going to be 1, 0. And notice what's going to happen is that point 0, 1 is going to go backwards into 1, 0. But you want to understand why Instead of just, okay, teacher told me they go backwards. Okay, you're not going to learn anything that way. So now go to the next one. You have ln, and again, that's ln of e. If you set that equal to x, that means e to the x equals e. What does x have to be in this equation? There's only one thing it can be. What is that? E to what power is e? 1. Okay, so that's this is going to end up being the point E, which is about 2.7. Okay, and that's going to be 1. And you could go through the same process on this. I'll do one more. If you're doing the ln, which is a base e of e squared equals x, I'm just writing that as a base e, then you would have e to the x is equal to e to the second. Well, the only thing x can be in this equation is 2. So that would be, you would have, remember, e squared is about 7.4, then you have 2 there. So these things are inverses of each other. So what's going to happen by the same argument, this is going to just be e to the -1, -1, and then e to the -2, and then -2 like that. So all the points go backwards. Just like the last problem, you had 2 to the x log base 2 to the x. Now you have e to the x ln of x because they're both base e. So if you plot this, you just plot like these 3 points right here, you'll get a good graph. So we have like 1, 0, over e and 1. E is about 2.7, up 1. E squared is about 7.4, up 2. So the graph of ln of x would look like the one that I'm drawing in green. So that would have kind of a similar result to the 2 to the x. Okay, and again, you can tell that those things are inverses because the points are backwards. And again, this thing is symmetrical about the line y equals x. Okay, that's the idea. Okay, all right. So that would be the way that you would go about doing and graphing logarithms is graph the exponential. Does that make any sense to you? Okay, because what happens a lot of times when students are graphing, like if I wanted you to graph log base 3 of x, to me the simplest way to graph that is to first of all graph 3 to the x, then flip all the points backwards and you got it. That's to me is the fastest, simplest, most efficient way to do that. Because otherwise you're just going to make, what I see students do all the time on a problem like this is there's a tendency to just want to use whatever number, and it doesn't work that way. What you'd want to do is you would want to do 3 to the x and then flip everything backwards and you got it. You see what I mean? It's way easier to do it that way, okay? Now let's fill this part out here. So e to the x is the red graph. What does it look like the domain of the red graph is? That's all real numbers, good. What does it look like the range of the red graph is? 0 to infinity, good. Okay, so remember, the domain of the function turns into the range of the inverse. Since the ln is the inverse, those are going to be the same. And again, the range of the function turns into the domain, so those are going to be the same. And the green graph, that matches it perfectly. The range of the green graph is all real numbers. It gets infinitely low, it gets infinitely high. The domain of the green graph is 0 to infinity. So it should match up with what you're expecting it to match up with, okay? Okay, so let's do, I'm going to do one that's got a transformation in it. I want to do probably a couple of problems that have got transformations in it now. Okay?
What if the range of e to the x be 1?
No, the range, e to the x is this graph here. Remember when we did the range of e to the x, that would be all the y values. Okay, what's happening on e to the x is it gets bigger, but if you look at the table of values we made, on this, the y's gets closer to 0. If you did 1 over e, 1 over e the second, 1 over e the third, those are numbers that are getting closer to 0, so that acts as a horizontal asymptote. Remember, range is this way. Domain is this way. The domain of e to the x is all real numbers. Because you can have any, you can do, an exponent can be anything. You may be getting those backwards. So the domain of e to the x is everything, all real numbers. The range is only there to there.
Right, that's what I was thinking, because isn't it start, because when it goes curves this way, wouldn't that be to work?
Yeah, that goes to 0 though. It's never going to touch the x-axis. It's just going to get closer and closer and closer to it. Okay? And what will happen is if you went to if you made your x's smaller and smaller, like if that was negative 100, you know what you'd have? You would have 1 over e to the 100, okay, which is 1 divided by a real big number, which just gets close to 0. So you're never, ever going to get any numbers below that x-axis for that reason. Okay, that's the idea. Okay, so let's go ahead and let's do these graphs on here then. Okay, so what I want to do with this is we're going to go ahead and instead of doing this graph, we're going to find the inverse, and we're going to do its graph. Okay, so let's go ahead and let's do the inverse. So you would want to start by writing down y equals ln x minus 3. Okay, because to me it's easier to graph the inverse of ln and then just switch all the points backwards. And that's what we're going to end up doing on this. Okay, so this is really y equals log base e of x minus 3. Okay, now what we're going to do is we're going to write this, we're going to find the inverse. So what you're going to do is you're going to switch the variables. So what you want to do now is go ahead and switch the variables. So that y becomes x, and the x becomes y, like that. Then we're going to write that in exponential form and then go from there. So what I'm going to have from here is this is going to be e to the x is equal to y minus 3. That's how you take the log and change it to an exponential form. Then if you solve this for y, you're just going to add 3 to both sides, which you can do in your head. So we're going to end up getting y equals, and I'm just going to write that as e to the x plus 3. Okay, so that's what your inverse is that right there. Okay, now that's what we're going to try to graph, as we're going to try to graph that, and we're going to think about transformations. Okay, all right, so your inverse, what you would have is f inverse of x on this problem is e to the x plus 3, like that. Okay, now what we're going to do is we can make a table of values for that if we want to, or you can just realize this. I'll see if you guys know this. So see, on the previous problem we graphed e to the x, right? Okay, we already graphed it. There's no need to do it again. What is that plus 3 going to do to that graph? It's going to shift it up 3, right? Okay, so what we want to do on this then is, since we're going up 3, let's just go to the table that we have here. I'll try to squeeze this on here so you can kind of see what I'm doing here. So what we're going to do is really essentially what happens, e to the x is this red graph. So the horizontal asymptote is going to move up to 3, isn't it? So you're going to have a horizontal asymptote, and every one of these points is going to get shifted up 3, okay, like this. So what we'll do on this then, when we're constructing this graph, let's go ahead and let's put a horizontal asymptote at now y equals 3. That gets moved up. So the x-axis moves up 3 like that. Now all these points, and these are the 3 key points right here that you want to do, is you just want to move all those things up 3. And we can use decimals on that. And I'm just going to kind of write these down over here. So I've got x, and I've got y is equal to e to the x plus 3. I'm going to use these same x values, so that's 0. And then 1 plus 3, that would go up to 4. So that point is going to shift from 1 to 4. The next point, you've got an x value of 1. If you do 2.7 plus 3, that's going to give about 5.7. Okay. Then the next point, you still have the same x value 2. And that y value is 7.4. So shift that up 3, that's going to take you up to about 10.4 like that. Okay. Now then you just need to plot those points, and that's good enough. So you'll end up having a point 0, 4. Okay, then you'll have like a point 1 and 5.7 approximately. And then you'll have a point over 2 and up a little bit above 10. So if you do that, that right there would be the graph of y equals e to the x plus 3. Okay? Now, if you're going to graph the logarithm, well, here's what's going to happen. okay, the horizontal asymptote turns into the vertical asymptote. So if you look at this problem we did above there, the x-axis is the horizontal asymptote. Well, if you flip it, then that becomes the vertical asymptote. So what we're going to do on this logarithm is we're going to just go over to 3. So we're going to go over to x equals 3, and then we're just going to put a vertical asymptote there. And then these points here, all I'm going to have you do is just flip those points there, and then you've got a good picture, a good viewing picture of this. So if you go over, this is going to become the point 4, 0. So just put a dot on 4, 0. This one is going to become the point 5.71. So you can just kind of approximate that. And then what you've got on that is you've got, let's see, 10.4 and 2. So if you go over 10.4 up 2, then you have a graph that kind of looks like this. Now, this can be a little bit misleading, is this graph gets bigger and bigger forever. So that thing doesn't approach that asymptote. This red line is the horizontal asymptote of that function only. That thing's going to go to infinity. What happens is you're not going to have a graph to the left of that vertical asymptote. So that's how that would be a rough graph of your logarithm. So that green graph right there would be y equals ln of x minus 3. Okay, like that. Okay, and that would be as far as you take that. Okay, now let's do the domain. All right, look at the graph of the function. Okay, the function is ln x minus 3. That's the function I gave you. Okay, the inverse was, that one was y equals e to the x plus 3. So look at the green graph. The green graph, okay? What does the domain look like from where to where? Just look at the green only. Where's it starting? At 3. And that's going on forever, right? Okay? So that's moving forever to the right. So what you would have here is the domain of f of x would be 3 to infinity, like that, okay? Now the range, don't even look at that horizontal asymptote. The range, that's going to negative infinity. Logarithms always do that. They go down to infinity and then they get bigger forever. This thing does not level off. It never will. So the range is going to be all real numbers, okay? Don't even look at that red line because sometimes students are kind of confused by that. That really affects how that behaves as you go to negative infinity. So that's all real numbers. And then what you do is switch these. So the domain of f turns into the range of the inverse. Okay? And the inverse is the graph in red, so you can tell that's 3 and above. Okay? And then your domain of your inverse is going to become negative infinity to infinity. So if you look at the red graph, that's going to be basically what happens is the domain's all real numbers. Okay? That's a little tricky to do that when you're doing graphs of logarithms with transformations. It's a little tricky. To me, the best way to do it is to find the inverse because it's easy to graph that. That's easier to graph than that is. Okay, and that's what I'm trying to teach you. So it's find the inverse, do the graph, flip the points. I mean, that's the best way, one of the simplest ways to graph a logarithm is to understand that exponent, that notation. Okay, let's do one more like that, and then I want to kind of go through some of these log equations here, and we'll be able to finish up 6-4 today. Okay, so let's see. On this, let's go ahead and find the inverse. So the function I'm giving you is you have f of x, and I'm going to write that as y equals 2 minus, and let's see, that is log base 3 of x plus 1. Okay, we're going to find the inverse of that. All right, so this is just like the last problem primarily. What do you need to do with the variables to find the inverse? Flip them. Okay, so this is going to be x equals 2 minus log base 3 of y plus 1. So what you have to do is you have to solve that equation for y. Now, you have to write that in exponential form. Before you can do that, though, you want to move that 2 over there. So you want to get that log by itself. So we would have x minus 2. And there's more than one way you can do this. This would be x minus 2 equals negative log base 3 of y plus 1. Now what I would do is you can't write that in exponential form until this negative goes away. So you need to make that go away. So probably the best way to do this would be to multiply both sides of this equation by negative 1. Probably the best way I could have done this problem in the very beginning would just be to move the logarithm to the left side at the very beginning. So what that's going to give you is that's going to give you negative x plus 2, or 2 minus x, and then this side is going to give you log base 3 of y plus 1. Okay, so that would be one way to start that then. Okay, now we want to write that in exponential form. So how does that go in exponential form? What do you say? 3 to the negative x plus 2 equals y plus 1. Okay, so that's going to say this 3 to this power. Let's just write that as 2 minus x. It doesn't really matter. And then that's going to be equal to y plus 1, like that. And then we can subtract 1 from both sides. So you can move that 1 over there, so you would get y equals 3 to the 2 minus x, and then minus 1 like that. Okay, that right there would be your inverse. So we'd have f inverse of x would be equal to 3 to the 2 minus x minus 1 like that. Okay. And what we're going to end up doing on this one is we're just going to make a table of values for that, graph that, flip all the points backwards, and we'll have the graph of the logarithm. Okay, that's the idea. Okay. All right. You guys understand what I did there, okay? Okay. Now you're doing inverses always the same way, flipping the variables, but when you're doing logarithms, you ultimately got to write that in exponential form. Okay. So let's go ahead and let's make a table of values for y equals 3 to the 2 minus x minus 1. I'm not going to do transformations on this. You could think of it that way if you wanted to, but I'm not going to really bother with doing that. I'm just going to pick some numbers for x and get enough good points that we can figure this out. So if we started at 2, I'm going to start like at 2, then I would just have 3 to the 2 minus 2 minus 1. So that's 3 to the 0 minus 1. We know anything of the 0 is 1, so 1 minus 1 is going to be 0. So we have a point 2, 0. So what's going to happen when you do 0, 2? That's going to be a point on the inverse, right? Okay, so we have that. Let's just keep going. Let's go to 3. So we have 3 to the 2 minus 3 minus 1. Okay, that's going to be 3 to the negative 1 minus 1. Okay, so that's actually 1/3 minus 1. And if you do that, that's a third minus 3/3 if you get a common denominator. So that's negative 2/3 like this. Now you're getting around the asymptote when you do this then. Okay, all right. Now I'm going to go this way. I'm going to go to 1. Okay, it's a little easier when you go this way. So we'll do 3 to the 2 minus 1 minus 1. Okay, so that's 3 to the first minus 1. 3 minus 1 is 2. Okay, we just probably get a couple of more points, and then we're probably in good shape to draw the graph of our log function. Let's go to 0. Then we'd have 3 to the 2 minus 0 minus 1. So that's 3 to the second minus 1. That's 9 minus 1. So that's equal to 8. Okay, so we get enough things on there that we're going to start getting enough points that we need. I'm going to do one more. I'm going to go to 4. So I'm going to do 3 to the 2 minus 4 minus 1. That's 3 to the negative second minus 1. 3 to the negative second is 1 over 3 to the second minus 1. So that's 1/9 minus 1. I'm going to get a common denominator, and that will give me negative 8/9. Just enough points to kind of show you what's happening on the problem. So what we've done is we got the inverse, and you can do the problem this way because it's easy to get points on that exponential function. Now what you're going to do, I'm not going to even have you graph these. I'm just, let's go ahead and put these on here. Let's go ahead and do both graphs. So let's go ahead and graph these points. So we have 0, 8. Then we have 1, 2, 2, 0. And then 3, negative 2/3. And then what's happening here, see these points right here, this is, I didn't write that right, that's -8/9. What's happening is this graph is leveling off at -1. So the graph of the inverse I found looks like that. Everything has been shifted down 1, and it's even been reflected over the y-axis because of that. Now to me, that's just as simple as just to make a table of values and forget the transformations. So that would be the graph of f inverse of x. Okay, now what you need to do is flip all these points around. You want to do 8, 0, 2, 1, 0, 2, -2/3, 3, and so forth. And then if you plot those, then you'll have what the graph of the logarithmic. Well, this is the graph of the function we're trying to do in the first place. So it would go like this. Okay, so what I do with this is this would be over 8, 0. So you want to put that on there. 2, 1, 0, 2. And let's see, from here we would end up, let's make sure I got that right. I got 2, 1, I've got 0, 2. And then I would just have this kind of approaching something kind of like this then. So you would end up having a logarithmic function that's been turned upside down. So it kind of does something like that. That's a really kind of a sloppy graph on there, but it does have the symmetry that you're going to expect on that. Okay, so that would be the idea. Okay, so I think I got all my points okay. So I got my inverse okay, it looks like. So that would be kind of the idea. The domain of f of x, so the domain of this logarithm would go like this. All right, the logarithm, and if you're doing 2 minus log, and let's see, that was a log base, was that a 3? Yeah, okay, so log base 3 of x plus 1. The way you find the domain is you set that thing greater than 0. So if you have x plus 1 greater than 0 and solve that inequality, you're going to have the domain is going to be -1 to infinity. Okay, that would be the function, the logarithm, and then the range is all real numbers. And then these things just go backwards, so the range of the inverse would be the same as the domain of the function. And then the domain of the inverse would be the same as the range of the function. So it would go like that. Okay? All right. Now, one thing about this, on graphs of logarithms, I don't generally test over transformations. I'd like you to do some of this on your homework. What I look at, the number one thing that I like to get students to do on an exam is, these kind of things like this example 1 where you have 2 to the x, log base 2 of x. No transformations on this, because transformations get a little bit complicated when you're doing that, but I do like you to do a little bit of that on your homework. So this kind of thing that I did right there, I don't generally test over that, but make sure that you know how to do something like example 1 or example 2 on a test. Okay, that's what I'm after, because I want you to know that logarithms and exponential functions are inverses of each other. That's what's important. Okay, let's finish up here by doing some equations in here, and we're going to solve some equations that have logarithms in it, and I'll have you maybe do a couple of these too. So what you want to do is you want to write these things in exponential form. So you want to make sure that your log is isolated. You want to have a log. You don't want to have anything in front of the log or anything outside of it. So if you wrote this in exponential form, how would this go on problem number 1? What would you say? 2 to the third equals 2x plus 1. Okay, that's what I mean when I say exponential form. So these problems are real simple to solve. Once you get these past the exponential form, then it's easy. This 2 to the third would be 8. Then you'd have 2x plus 1, like that. You'd subtract 1 from both sides. So you would end up having 7 is equal to 2x. Okay, then you could divide by 2. So you would get x is equal to 7 over 2 like that. Okay, that's the answer to the problem. Now, I want to check these, because if you learn how to check these, you will understand this stuff much better. So let's check this and write this down in your paper. I want you to write down the checking too. Let's go back to the original equation, and where we see a 2, just plug in the answer 7/2. The fractions are going to work their way out of the problem anyway. Okay, so we're going to verify that that's equal to 3. Okay, well, here's what happens. The 2's cross out, so you're left with log base 2 of 7 plus 1 or 8. Can you guys look at that and tell me that's right? That's what I want to know. Yeah, how come? Why is that right? Because 2 to the third is equal to 8, right? That's why. So you're right. Remember, if you get that, when you're doing a logarithm, you're saying what power of 2 is 8? 2 to the third is 8. Okay, so that's right. That's what you do to verify that you have a correct solution on your problem then. Okay? Okay, next one. We'll do this basically the same way. So let's do, we write this as x to the third is equal to 1/8. Okay, that is the exponential form. We learned how to solve this equation way earlier in the semester. What do you do to both sides to make the x to the third just become an x? You do the what thing? The third root of both sides, right? If it's x squared, you do square root of both sides. So what you're going to do is the third root of both sides. You don't need to do the plus or minus on that or anything. So that's x equals, and then you're doing the cube root of 1 over the cube root of 8. What's the cube root of 1 and what's the cube root of 8? 1 and 2. So that would be x equals 1/2. Okay, so that would be the answer to that problem. Okay. All right, let's check and verify that also. Okay, so what you want to do is go back to the original equation and replace the x, which is the base. That would be 1/2. So we would have the log base 1/2 of 1/8 is equal to 3. Now here's how you tell this is right. It turns out it's real easy. You just take exponential form. How does exponential form go? 1/2 to the third equals 1/8. Let's see if that isn't right. What do you think? Yep, okay, because 1 to the third's 1, 2 to the third's 8. So that's equal to 1/8. So it's actually very easy to tell you're right on these type of equations. If you plug it in and take a little bit of time, you can verify that you have the right answer. If you take the time to do this when you're learning this stuff will make a lot better sense to you. Okay? All right, let's go down to this number 3. Let's do that, and then we'll finish up with some exponential equations. Okay, so this one we're going to do 5 to the second is equal to x to the second plus x plus 4. Okay, this is a type of equation you've learned how to solve earlier this semester. That's 25 equals x squared plus x plus 4. Okay, that is a quadratic equation. What do I need to do next? One side needs to be what? 0. Good. Okay, so you got to remember things we learned a long time ago. So you need to do that. So now you get 0 is equal to x squared plus x minus 21. Okay, now you have either you're going to factor it or you're going to go to the quadratic formula. This one looks like a quadratic formula one, which is too bad, but let's deal with it. Okay. All right, so we would have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, if it doesn't factor, that's what you got to do on a quadratic equation. Okay, so if we work that out, we're going to have b is 1, so we would have negative 1 plus or minus b squared. B again is 1. A is 1 also. A is the number in front of x squared. C would be negative 21. Then that would be all over 2 times a, or 2 times 1 like that. So what you'd end up having is negative 1 plus or minus square root. And if you do this, you could use your calculator. That's actually 1 plus 84 all over 2. So that's negative 1 plus or minus square root of 85 over 2. Okay, like that. All right, now I'm not going to check this. I probably should, but I don't want to take the time to do that. So that would be the solution of that equation would be that then. Okay, like on an exam, problems like this, what I prefer to do is log equations where they factor, because then you can do the checking on that a little bit more efficiently. Okay. Okay, let's finish up here with these exponential equations and run through these. Now we do this in this section, we do these a certain way. Then when we get to 6.6, we end up doing these a little bit different way then. Okay, so what we're going to do on this is we have e to the negative 2x is equal to 1/3. Okay, now what we try to do in this section is we try to just write these in log form. So we're going to try to write these in log form. Okay, so the base on this is what? E. That's the base of the exponent. That's the number that's being raised to a power, so that's log base E. Okay, remember, anytime you're doing a logarithm, the exponent is the answer. So what you would say, if you write this exponential form into log form, you're going to get log base E of 1/3 is equal to 2x. All right, was that a negative 2x? Yeah, that would be negative 2x. Okay, so you go like that. All right, so I'm taking the exponential, writing in log form. Okay, what do you do to solve this for x? Got to get x by itself, so what do? Divide by negative 2, right? So really all you would have to do on this then to get your answer is just do this. So that would be x. Remember, if you have a log base E, you can write that as ln of 1/3, then divide by negative 2. Now that's the exact answer to the problem. All these problems on this section, we're going to change the exponential equation into log form and get our answer that way. And again, later we'll learn a little bit different way to do that, okay? Okay, the next problem, you want to start this one by dividing by 5. So you have e to the 2x is equal to 7/5. Okay, you don't want anything in front of that exponential. Okay, now what you got to try to do is, like I did on the last problem, try to write this as a log. Okay, what's the base of this log? E. Remember, the answer to a log is the exponent. What's the exponent? 2x. That goes on the other side. Then you have 7/5 like that. So what you would have is you could write this as ln of 7/5 equals 2x. Then you just divide both sides by 2. So your answer would just be written as x is equal to natural logarithm of 7/5 all over 2. Okay, and that would be it. Okay. All right. Now from here, I'm going to do one more like this. And let's see, divide that by 2. So that would be 10 to the 2 minus x is equal to 5/2 like that. So you got to start that problem the same way. Now again, you want to write this in log form. So what is the base of this going to be? 10, okay? Your base is that number. The answer is the exponent. The answer to a log is an exponent, so the 2 minus x goes there, and then the 5/2 goes there. So the key is you got to take the exponential function and write it as logarithmic. Now let's solve this for x. Now here's how I'm going to do this. I think it's easier if I move the x over here and move the log over there. It's less work if you do that. So if I move the x, that's going to give positive x. Then I leave the log where it is. Remember, if it's log base 10, then you don't have to put the base, because that will be understood to be log 5/2. And then we still have the 2 here like that. So that would be a minus there, and then the plus 2 that's there. So what I did was I just moved the x to that side to make it positive, moved the log to that side to make it negative. So you could write the answer to that problem like that. That would be the idea. Okay? All right? So that's the idea. Let's finish up these ones on the next page here. I'm kind of whipping through this, but I want to get this done a little bit easier here. Okay, so let's do the last one here. Let's see. Write it in exponential form. So that's 3 to the second equals x squared plus 1. Okay, square that. That's 9. Oops. So that's going to be 9 is equal to x squared plus 1. Okay, subtract 1 from both sides. So that's going to give 8 is equal to x squared. Then I can do square root of both sides, and you do have to have the plus or minus there. And then you can break that up into 4 times 2, like we learned earlier in the semester. So that would be plus or minus 2 root 2 is equal to x. Okay, now when you check this, the number one thing you have to check for, you don't have to check the whole thing, but you got to make sure this argument does not become a negative number. So I want to just show you kind of at a minimum what you got to do. So if you just did positive 2 root 2 squared plus 1, that gives you a positive number. Because if you take anything square, that gives positive, so that works okay. Then if you do negative 2 root 2 squared plus 1, that's also positive, because if you square this number right here, it becomes positive, and add 1 to it. Okay? So that answer to the problem, both of those things are going to be okay. All right? Then this last one here, you want to write this in log form. Okay? So what's the base of this logarithm? E. What goes on the right side of the equal sign? Negative 2x. That's the exponent. There you go. Now all you got to do is just solve that for x. So you would have ln of 1/3 is equal to negative 2x divided by negative 2. So your answer would just be x is equal to natural logarithm of 1/3 all over 2 like that. Okay, and I realize I kind of whipped through those things at the end, but I needed to get that done because this is where your test next week stops, is at 6-4. Okay, so what we're going to